scientific knowledge is constantly evolving and changing, and so this is one of those examples where we go from the Bohr model to something that we call the quantum mechanical model of the atom. So the Bohr's model was great. It demonstrated how electrons could absorb and release energy. And it also explained how atomic emission spectra are created. However, it didn't really explain why electrons should exist in fixed orbits or fixed circular orbits. And there was no explanation of why there would not be an infinite set of orbits. And so scientists were set out to kind of answer these questions. And so one of those was the de Broglie equation. And so back to that photoelectric effect, remember that if the frequency was high enough when a light was shined at a metal, it could eject an electron. And so that photoelectric effect supported that light can indeed behave like a particle rather than a wave. So scientists began to wonder if matter that usually acts like a particle could really act like a wave. So anytime we're really referring to a particle, what we're doing is we're really talking about an electron. So Louis de Broglie in 1924 was a French scientist. He came up with this equation that says the wavelength is going to equal Planck's constant over mass, and make sure it's mass in kilograms, and then velocity, and it's the object's velocity and not frequency. And so remember, with Planck's constant formula, we had energy equals Planck's constant times frequency, which also kind of look like a V. So be careful that you make sure that you're not using the wrong V. And so here it's representing velocity. So to practice using this equation, it's an electron with a mass of 9.11 times 10 to the negative 31st kilograms, so notice our mass is in kilograms, is moving at nearly the speed of light. Using a velocity of 3 times 10 to the 8th meters per second, calculate the wavelength of this electron. So remember the formula says your wavelength equals Planck's constant over mass times velocity. So in this case, we know Planck's constant from the last video is 6.626 times 10 to the negative 34th. All of that over the mass of that electron from the problem times the speed of light. And you will get a wavelength of 2.42 times 10 to the negative 12th meters. Be careful when you do this math that you put your numerator in an extra set of parentheses as well as your denominator so that it does the order of operations correctly. So this wavelength is so short, we can't actually detect it with scientific equipment, even modern scientific equipment. So what this did do was it showed that an electron confined to a particular orbit can only move so that the wave-like path of the electron fits into the orbit. This demonstrates that frequencies of electrons are quantized. So using Planck's equation, scientists demonstrated that electrons can only exist at specific energies. So this really supported Bohr's ideas. So by fitting into specific energies. The path, the wave-like path here, fits into this particular circular orbit because the beginning and the end do not overlap. They start and finish together. Whereas in this wave out of phase, is if you go through and trace it, you would see that in these two paths don't actually meet up, and so this right here would be a possible orbit for an electron, whereas this one would not be an orbit because it's out of phase. It's got that little overlap there. And so remember, this would be like our ladder example. We would be falling in the middle of the rungs, where over here everything is hitting the rungs perfectly, and so this would be a possible orbit. So this brought up the idea of quantum mechanics. And quantum mechanics is the study of the motion of objects that are atomic or subatomic in size. And thus they demonstrate something called wave-particle duality. And wave-particle duality means that it could either be a wave or it can behave like a particle. So classical mechanics, this is usually what gets studied in like a physics class, is something that studies large objects, large enough to be seen unaided. So no microscopes needed. The size and the mass of the objects cause them to not be affected by quanta of energy. The objects do not and will not demonstrate that wave-particle duality. They'll either behave like a wave or they'll behave like a particle. In quantum mechanics, you're studying particles that are the size of atoms or smaller. And the small quanta of energy can greatly affect the objects of study. And like we said down below here, the objects will demonstrate that wave-particle duality. So they can act like a wave and a particle almost simultaneously. So with the idea of quantum mechanics in mind, there was this principle that states that it is impossible to determine simultaneously both the position and the velocity of a particle. And this is referred to as the Heisenberg uncertainty principle. In order to detect an electron, photons of light must interact with that electron. And any interaction of electrons and photons causes the path of electron to change because both electrons and photons have the same energies. I kind of think of this as like a pool ball sitting on the pool table. If you hit one, it's going to change the direction and energy of the both balls involved with the collision. And so the big thing here with the Heisenberg uncertainty principle is that it is impossible to know both the location and velocity of a particle at the same time. You can either know one or the other, but you cannot know both. So in 1926, an Austrian developed a really complex math equation, Erwin Schrödinger, to accurately describe the behavior of the electron in a hydrogen atom. He used the wave-particle duality idea. So based off of this Schrödinger equation, he was able to develop the quantum mechanical model. The solutions to this equation are called wave functions. the great thing about this quantum mechanical model is that it gives the probability of finding an electron at a given point. And it also states that electrons do not travel in circular orbits, like Bohr thought. Instead, the location of electrons are referred to as the electron cloud. So, electron clouds have highly variable densities. So, if it is an area with high density, it means that there's a high likelihood of finding an electron in that area. If it's low density, there's less likelihood of an electron being in that area. So we call these, if you look at this diagram, this black region would indicate a very dense area, and as you move out into the lighter gray and the white area, the change in color there indicates going from a high density to a low density. So your greatest likelihood of finding an electron is usually closest to the nucleus, and your odds of finding an electron decrease as you move away from the nucleus. So instead of them moving in circular orbits, they actually have a three-dimensional region of space that they occupy, and we call those orbitals. And there's a really good chance of finding an electron in these three-dimensional orbitals. And we'll talk more about those in the next video.